SN1 is very similar to SN2, except that the mechanism is different. In SN1, what happens is the rate-limiting step is just the leaving group leaving. And so there's only one component in the rate-limiting step, and that is the substrate. So we call it substitution nucleophilic unimolecular because there's only one compound in the rate-limiting step. Okay, the first step in the SN1 mechanism is that the leaving group leaves. And this is shown down here at the bottom, where this is the bond between the carbon and the leaving group, and the electrons leave with the leaving group to give you a leaving group with a negative charge. This can be actually where the leaving group has a positive charge, so when it leaves it's neutral, but we'll look at that later. For now, just think the leaving group leaves with the electrons, giving it a negative charge. When it leaves with the electrons, notice that you get a positive charge on the carbon. This is the carbocation, and you remember the stabilities of the carbocations, that tertiary is more stable than secondary, which is more stable than primary, which is more stable than methyl. And remember also that the vinyl carbocation is more stable than a tertiary carbocation. Because there are only 3 areas of electron density around that carbon, this is then a planar geometry. So the carbon has an empty p orbital that is perpendicular to the plane of the bonds. And now when we go to the next step, you're going to find that the nucleophile can attack from either side. But let's talk about this step a little bit more first. This is the rate-limiting step. And if you notice, you will see that the only thing that is in this rate-limiting step is the substrate. So that is all that the rate-limiting step depends on. So anything that affects the substrate or the ability of the leaving group to leave or the stability of the carbocation is going to affect the rate of this step. This is the rate-limiting step. Only one compound participates in it, and that's why we call it SN1. Okay, the intermediate is this planar compound. It's symmetrical, meaning that this side of the compound is the same as this side of the compound to any kind of nucleophile that will come in. Therefore, the nucleophile can come in from this side, or it can come in from this side. Now, this is called the counter ion. The leaving group is called the counter ion to the carbocation. And because they're still attracted to each other because of opposite charge, it does tend to stay close and can sometimes get in the way of a nucleophile attacking from this side. So realize that can sometimes reduce the ability of the nucleophile to attack from this side. But in general, we consider either side to be equally likely to be attacked by the nucleophile. As a result, you can get 2 products if a chiral carbon results, and those 2 products will be enantiomers, so a racemate would form. Because a carbocation forms in an SN1 reaction, we can have the complication of carbocation rearrangement. If I look at this substrate and this bromide leaves, it will leave a positive charge behind on this carbon. See, there we're showing that over here. So this is a secondary carbocation, which is less stable than a tertiary. And if you remember, from previous chapters, the carbon can walk over to here. We called that an alkyl shift. When that carbon walks over to the secondary carbocation, it will leave behind a tertiary carbocation. That tertiary carbocation is more stable, and so this is more likely to form than stay as a secondary carbocation. If there's water around, what can happen is the water can attach itself, come in as a nucleophile on that carbocation, and then what we would get is this protonated alcohol would result, and the product would then be that the proton leaves and leaves an alcohol behind. Here's an example of an SN1 reaction. Notice there's no rearrangement here. Here is a tertiary alcohol. What happens is you protonate this alcohol and it can leave as a leaving group. When it leaves as a leaving group, it leaves a positive carbocation right here, and then the bromide comes in and replaces the alcohol group. Notice, this was an SN1 reaction, so what are we getting here? We are getting racemization, because it's just as likely for the bromide to come in from the top as to come in from the bottom. Here's a secondary carbocation, and what happens here is that the leaving group leaves, it puts a positive charge here, and then an alkyl group walks over and puts a positive charge on this carbon right here. Then what happens is you can get that you have an enantiomers form or racemate form because there was a chiral carbon there once you have the bromide attached to the carbon. So go ahead and look at this reaction. This is an SN2 reaction. No racemization is going to occur because you're not going to get a chiral carbon. Figure out what is the product of this SN2 reaction. The product of this SN2 reaction is where the nucleophile comes in and displaces the bromide. So the bromide leaves and the sulfur, the methyl sulfur group comes in and replaces it. Okay, determine what is the product of this SN1 reaction. Here is the nucleophile. The oxygen on the methanol is a nucleophile, and the bromide is the leaving group. Okay, this is going to be a simple SN1 reaction, so what has to happen first? The bromide has to leave. That forms a carbocation right here. Then the oxygen has non-bonding pairs that come in and jump into that carbon with a positive charge. When it does, you're going to have the oxygen will then have a positive charge, and the bromide will then come and remove a proton from that oxygen. What results is this product. The product is not chiral. This side of the molecule is the same as the other side. Okay, when you have an SN1 reaction, what happens is there are two steps because a carbocation intermediate forms. First, the leaving group leaves. Okay, that forms the carbocation right here. Then the nucleophile can come in from either side, and then it comes in and boom, you get the new compound formed. So notice it is two steps. The slow step is the leaving group leaving. The energy of the transition state here, though, is determined by the energy of the intermediate. So if you have a high energy intermediate, the transition state is going to be way high also. If you have a low energy intermediate, the transition state will be lower. So the rate equation depends on the slow step, which is the formation of the carbocation. The only thing in that step is the substrate. So the rate equation for this reaction is rate is equal to K times the substrate. Notice the nucleophile does not matter. The whole reaction depends on the substrate and the things that affect the substrate. So when we look at this reaction, we keep that in mind, that it's only the characteristics of the substrate that control the rate of this reaction, and anything else in the reaction that might affect the energy of the transition state of reaching the carbocation.